Welcome to the Journey Chez Chem. Well, please do the 2 warm-up questions to the best of your ability, and we will discuss them in a moment. And number 1, the first question that I must ask myself is this a weak acid or is it a strong acid? Very, very important question. Because if it's a strong acid, I won't go through this process. However, nitrous acid is a weak acid. And therefore, I know that it's going to have some dissociation, but I don't know how much. Well, I'm starting with a 0.22 molar solution. And initially, nothing has dissociated. Then I know that some small part of it will dissociate, and it separates to give me the same amount of the hydrogen as the nitrite ion. Then I add up those columns and I get 0.22 minus X because some of it has dissociated and come over here to form X and X of those ions. Well, I'm going to assume that this amount dissociated is less than 5%. We always assume that, and then we check it to make sure we're okay with our assumption. And then I write my Ka because we're talking about an acid. Well, my Ka is the products, and we don't have to worry about any coefficients in these problems, divided by my reactant. And only the nitrous acid is the one included here because water is a pure liquid, and we do not include pure liquids or pure solids in the equilibrium expression. I always want to see this expression written out. And then I substitute in the values. Well, I have X of the hydronium and X of the nitrite. Well, that gives me X squared, divided by my 0.22. And you'll recall that we did eliminate the X here. And I know that this is equal to my Ka, and I'm given that value. And that value is 4.5 times 10 to the negative 4. Then I solve for my X. I multiply my 0.22 times my constant, and then I take the square root to undo the square. And I come out with X being equal to 9.9498 times 10 to the minus 3. Well, this X represents my hydronium ion. And I always take these numbers to the hundredths place. And therefore, my final answer is, where shall I write this? I'm just getting I'll write it here. My X is equal to 9.95 because this 9 rounds the 4 up times 10 to the minus 3 molar hydrogen ions. You'll recall that hydrogen ions and hydroniums are used interchangeably. Well, that's not my final answer. The question is asking for the pH. And I know that the pH is equal to the negative log of the hydrogen ion concentration. Therefore, I take the log of this number because I'm putting it in here. And when I take the log of that number, I get the pH is equal to 2.0021. Then I take it to the hundredths place, and my final answer is 2.00 is my pH. Now, I also need to figure out the percent that it is dissociated. So I take my number of the amount that it's dissociated, and I divide it by my original amount, and times 100. And when I do this, I get 4.5%. That's pretty close to 5%, but we're safe. So I don't need to worry about that. I am less than 5%. And that's how you do number 1. In number 2, we are determining either the concentration of the ion or the pH for this information. Well, here we're given pH, and we want to find the hydronium or the hydrogen ion concentration. And therefore, you'll recall that this is 10 to the minus 5.65. And when I do the math here, I notice that I have a log button on my calculator, and above that is 10 to the x, which is what pH is. It's 10 to the minus pH. That's what we have. And because most people don't want to deal with numbers like this, that's too difficult. We just want a regular number between 0 and 14. So we use logarithms. Well, when I do this, I find my number is 2.2387 times 10 to the minus 6th. Then I round to the hundredths place. 2.24 times 10 to the minus 6th molar hydrogen ions or hydronium ions. That's a +1. Now here I'm given a pOH, and I know that the pH plus the pOH is equal to 14. So I will subtract it first. And I get a pH of 10.75. Then I make the number negative and take the inverse log. And I come out with 1.7782 times 10 to the minus 11. Well, the 8 rounds the 7 up. And I get 1.78 times 10 to the minus 11 molar hydrogen ions. In these two problems, I'm going directly to the pH, or in this case, the pOH. I notice that it's hydrochloric acid, which is a strong acid and has 100% dissociation. And that's why I can just take the log of this number. And when I do that, I get 3.4571. The 7 rounds the 5 up, and my final answer is 3.46 is my pH. Now here I'm given a hydroxide, and therefore when I take the log of this number, I get a pOH. And my pOH is 0.8239, or 0.82. Then I subtract from 14, and I get a pH of 13.18, which would show that it is very basic, very alkaline, because it's a base. Well, that makes perfect sense. Well, we have two things to cover now. I'm going to talk to you a little bit about the lab that we did and clarify some of the ideas that we need to go over so that you can write up that lab. And then we'll talk about acid-base theory, Bronsted-Lowry, Lewis, and Arrhenius. So I'll be right back. In the lab, in the analysis portion, we must, in the first part, determine the concentration of the base. And we call that standardizing the base. And we're going to use that base then in the second day, or we did use it the second day, and we had to know the concentration of that base. And that's what the titration allows for us to do. Well, we know that we were given a 0.1 molar solution of the hydrochloric acid, and that was in the procedure. And I always rewrite these to be 0.1 moles in 1 liter. That's what that means, of the acid. Well, I want to know how many moles there were in 10 milliliters. And I must change my 10 milliliters to liters because my value here is in liters. And I must be consistent with my units. And when I solve this, my x is the number of moles that are in those 10 milliliters. And it comes out to be 0.001 moles of my hydrochloric acid. Well, when it turns pink, we know that we have an exact amount of the base as well. So the answer for the moles of the acid and the moles of the base will be the same. Then, to get the concentration of the base, you are given an equation. The molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. And what we're looking for is this molarity of the base. And you know, it's always good to rearrange the equation. And therefore, the molarity of the base equals the molarity of the acid times the volume of the acid divided by the volume of the base. That will give me the molarity of the base. And the volume of the base is going to be however much it took to get that pink color. That would be the volume. And you could use milliliters in both cases. You have 10 milliliters here and milliliters here. Because they're both milliliters, that's fine. You don't have to change it. But this would be in part A, the volume that it took to get the titration to the pink color. And that will give you the concentration, the molarity of the base. Then I take that molarity of the base in the second part. I have the molarity of the base, and that equals the moles of the base divided by 1 liter. And I want to know the moles that it took to get pink. In the second part was a different volume that it took to get pink. Now I'm going to either use the best pink color or the average of those. And it may very well be the average of how many milliliters. And in this case, you will need to put this value into liters because we have different values for the volume and we need to be consistent in liters. All of our volume should be to the tens place. And then we're finding the molecular weight. For part B, that's what the purpose. We're finding the molecular mass of the unknown acid. Well, we know that we weighed out 0.50 grams, and we're going to divide it by the moles that we find here. Grams per mole is my molecular mass. I believe that should help you pretty much figure out what we did in the titration lab. I know you can do it. We had some fun doing it. And in a moment, I'll be right back to talk to you about acid-base theory. We have been talking about acids and bases for quite some time. However, there are 3 theories that are the basis of understanding how acids and bases operate. The very first theory that came up was Arrhenius, and Arrhenius stated that acids form hydrogen ions in water, and bases formed hydroxide ions in water. Well, that just was not sufficient, so Bronsted and Lowry came up with another idea about how we can handle acids and bases. Well, first we need to understand the term amphoteric. An amphoteric substance is one that can act as either an acid or a base. Just like being ambidextrous means you can write with either hand. Well, amphoteric, ammonia and water are both amphoteric. And we've learned up to this point that water was not an acid or a base. However, it can act as one or the other under certain specific situations. Well, let's first take a look at ammonia and water. Both of these are amphoteric, which makes it a very good example for what can happen in a Bronsted-Lowry reaction. And we are talking in Bronsted-Lowry about the hydrogen ion, which is called a proton. And you'll recall from the first day of school, we had the hydrogen atom and it had 1 proton and no neutrons because its mass is 1 and the mass is the protons plus the neutrons, and therefore we have no neutrons. Then we have the electron that is around the center of the atom, and we know that it does not go in a circular fixed pattern. However, this is a very simplified model. Now, when hydrogen becomes an ion and it loses that 1 electron, well, then all that's left is the 1 proton. And therefore, we can call the hydrogen ion a proton. They're the same thing. So don't be too put off about proton acceptors and proton donors. We're just talking about what happens to the hydrogen. Well, here in the case, let's look at ammonia behaving as an acid. Well, when it behaves as an acid in the Bronsted-Lowry theory, that means that it is going to donate a proton. Well, when it donates a proton, it's going to give up a hydrogen. So if we take a hydrogen away from this ammonia, we're going to have NH2 with a -1 charge because we've only taken away 1 of those electrons. And remember, when it was together, it was paired up. And therefore, this particle that is obtained after we donate the proton is called the conjugate base. Conjugate. Gotta learn to spell here. Conjugate base. So the acid gives up a hydrogen and becomes the conjugate base. Then water is going to act as a base. Well, a base is going to accept a proton. Well, if we add a hydrogen to this, we get the hydronium ion. And then that would be my conjugate acid. It's important to notice here that at this point, we're talking about pairs, conjugate pairs. The acid, the conjugate base. The base and the conjugate acid. If I looked at it in reverse, this would be my base and this would be my conjugate acid. It depends on which direction we're going. And this would be my acid and this would be the conjugate base. However, for our purposes, the acid and the base will always be reactants and the conjugate will be a product. Now let's look at ammonia as being a base. Well, when it's a base, it's going to accept a proton. It's going to accept a hydrogen. And therefore, it will become the ammonium ion. That would be its conjugate acid. And if I look in reverse, I see that this hydrogen has been given up to the ammonia, and therefore this is my acid, and this would be the conjugate base. This becomes very, very important. Conjugate pairs are very, very important. Water then is going to act as the acid, and therefore it's going to donate a proton. And when it donates a proton, it's going to become the hydroxide ion. It gave up a hydrogen. So you look in the equation and you say, where did the hydrogen go? Well, this ammonia lost a hydrogen, and this ammonia gained a hydrogen, and therefore they are the pairs. And when water acted as an acid, its conjugate base is the particle that you get after it donated that hydrogen. Remember, the proton is the hydrogen ion. So we're looking for where does the hydrogen go. That's the interesting part about these pairs. Bronsted-Lowry has conjugate pairs. Finally, the next one that we have is the Lewis acid-base theory. Lewis, you'll recall, Lewis dot diagrams when we did the shapes of molecules. Well, when we have electron dot diagrams, those would be part of the Lewis acid-base theory. Now here, if we have ammonia, and in these it's very important that we draw dot diagrams. You may have to go back and review how many dots things have. Well, nitrogen is my center atom. I have 5 dots, S2, P3. Hydrogen has 1 dot, and therefore I get this trigonal pyramidal shape. Well, a Lewis base is an electron pair donor. Electron pair donor. And remember, a Bronsted-Lowry base was a proton acceptor. One thing we're talking about protons which are positive, and the other we're talking about electrons that are negative. Then I have boron trifluoride. Well, boron only has 3 dots, and it's happy with 6. And fluorine has 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Well, when we look at this structure, we see that there is a space here where it could accept an electron pair. A Lewis acid is an electron pair acceptor. A Bronsted-Lowry acid is a proton donor. That's the big distinction between those two theories. Now, this Lewis theory can cover any kind of reactions, and what happens here is this nitrogen donates these 2 electrons to this boron where it has an empty space. And then they hook together. The nitrogen combines with the boron. And then we have the fluorines and the hydrogens. And we have one large molecule. And that's what happens in the Lewis theory. Now, all you're going to need to be able to do is draw the dot diagrams and say, will this behave as a Lewis acid or a Lewis base? And when we have a filled octet, we're going to have a Lewis base. If there is space to take an electron pair, then it will be a Lewis acid. And if something has a double bond, that double bond could be broken and make room for an electron pair. And you'll have some practice on this. And those are the three theories. We'll have some practice and we'll go over that. And that's the last of the notes that we need to take. So we're just going to practice now. You have a worksheet tonight. We'll practice it tomorrow. Then we'll have a little bit of review and you'll be ready for the assessment. And then we'll be ready for the final exam, the semester exam. I know you're looking forward to that. And we've learned a lot of things this year. Well, I can't wait to see you tomorrow. Thanks for being here. Bye.